Welcome back. So I'm glad to see you to come to lecture 9 now that we are done with Kohn-Sham, Hohenberg-Kohn, and in lecture 8 we introduce the LDA. LDA is a good example of an exchange correlation functional, and for the remainder of this course we are going to develop exchange correlation functionals in addition to some lectures which will be devoted on tricks and how we actually run DFT calculations, but we'll get that to the point. We'll get to that point in due course. So today I want to talk about the bandgap problem in DFT. I didn't talk about bandgap as a limitation of LDA, but I'm going to mention that now because it's an issue in its own right. So yeah, I think it's important before we get started to be reminded about some definitions. That's very useful. The first thing is, as you noticed in this course, we have been talking about molecule, we've been talking about solid, but we can also think about interaction between solids and molecule, like on surface, for example. And it's also useful to realize that sometimes some jargon is different when we talk about molecules and when we talk about solid, for instance. So a first example is this description of this occupied state, which I represented schematically as those thick lines. These are states that are occupied by individual electrons, and the unoccupied states, which are described by those dashed line, dotted lines. I also plotted on this curve, on this schematic, the vacuum level, which is actually the energy. Essentially, it's an electron. When an electron is in vacuum, that means that that electron does not feel the presence of the material at all. Okay, so the reason why I mentioned this jargon difference between chemistry and which we use in molecules essentially, and solid, like conduction and valence band, is because those states that are the highest occupied and the lowest occupied have slightly different name if you talk about molecules and if you talk about solids. So, for example, in chemistry, we would call about a HOMO, which is the highest occupied molecular orbitals. It's just exactly what it means. And the LUMO, the lowest unoccupied molecular orbitals. In the literature, you see those LUMO and HOMO used as well sometimes for solids, even though obviously it only works strictly speaking about molecules. But for solid, we rather use a valence band, so and the top of the valence band for the highest occupied state, and the bottom of the conduction band. Conduction being the bottom of the conduction band being the lowest energy closest to the occupied state. So this is something you probably know from your other courses, but this is also always useful to remember this. Then we talk about the energy, which is called the electron affinity. And the electron affinity is essentially the energy you need to provide, that you get when you take an electron from vacuum, so an electron that does not feel any other material, and you bring it to the material. Of course, if you bring the electron to the material, the lowest energy state that it can occupy is the conduction band, or the lowest unoccupied molecular orbitals for molecules. This is called the affinity. So it's pretty easy to remember that word, because affinity means how well does the electron has affinity to join the material. Then we have what we call the ionization potential, which is the energy you need to ionize your system. So the first ionization potential, essentially, that's the energy that you need to convey to an electron to bring it to vacuum. And of course, that lowest energy is for the electrons. This is the highest energy, so from the HOMO or the valence band. This is called the ionization potential. And of course, we talked about the band gap. The band gap is that energy that's between the highest occupied molecular orbitals and the lowest unoccupied molecular orbital, or the energy between the valence and conduction bands. I am not going to use all the words going forward, but you see now the difference between the two. And that energy gap, of course, is that distance that we have there. And we see from inspection that that gap is basically the affinity minus the ionization potential. So this is the definition of a band gap. This would be if we have this single electron picture that we have there, that would be what we would find, for example, in Hartree-Fock. Another way to look at this, which is equivalent, but it's always useful to think about those differences, is that the ionization potential can be written as En minus 1 minus En. Let me explain that because we are going to use this in this screencast quite a bit. En is the energy of the system with n electron. So En minus 1 is the energy of the system with n minus 1 electron. Obviously, you can convince yourself pretty easily that the ionization potential will be that difference of energy between the system that has lost an electron, so E minus 1, minus the energy that you had before it lost an electron. So that's the ionization potential. And similarly, we can calculate the electron affinity using a similar approach, where in the affinity case, it's the energy between the system that has gained an additional electron relative to the system that has not gained the additional electron. So as a result, A is equal to En plus 1 minus En. These are basically reminders. This is actually useful. Frankly, it's easy to forget how it works. So that's why I like to present this slide. You can, if you're not convinced, take a minute to convince yourself. Maybe pause the screencast at this point and convince yourself that this is true. So now what we can say, I'm going to say this again with slightly different words just to make sure it sinks in. If we take an electron from the valence state, from the state V, the L epsilon V, and remove from the system, we see that that state EV is going to be indeed the energy of the system with n electron minus the system of n minus 1 electron. Right? This is where the electron would go this is where the electron would go, the last electron would go essentially, right? Between a system that has n minus 1 electron and a system that's n electron. This is what you do if you add electron one at a time. And similarly, the conduction band, for adding an electron, the energy of the conduction band will be the one that's obtained from basically adding an electron to the system with respect to a system that has only n electrons. So this is epsilon c is obtained. Now we can find by using this approach, basically defining what the energies of those conduction and valence bands, we can calculate the band gap, and the band gap will be the energy of the conduction band minus the valence band. We say EC epsilon c minus epsilon v because we know epsilon c is obviously larger than epsilon v at 0 kelvins. It's certainly for sure, and then we get the difference between the two is obtained, of course, directly. And of course, you could get exactly the same answer if you were using the definition of the band gap with respect to A and I, the band gap being A minus I, and you would get, of course, the same answer. But what matters here, and I'd like you to remember this for the rest of this screencast, where I am going to explain to you the origin of the band gap problem in DFT, is that in order to calculate the band gap, we basically need the energy of three systems. The three systems are the system with n electron, the system with n minus 1, and the system with n plus 1. So that's basically the most important result, really, of this first few slides is this equation in blue on the left. And so this would be for this energy here. Now, for the fact that epsilon v is the ionization potential is something that comes from Koopman theorem from this paper from 1934, just 90 years ago. And the Koopman theorem showed exactly that in Hartree-Fock theory, this is the case. The HOMO state is indeed the energy of the ionization energy. So that's the idea. In Hartree-Fock, this single electron, since we build the solution from single electron solution, this is actually quite clear that this would be the case. And again, we can calculate the band gap like this. Now, one thing you should know is that Hartree-Fock is not that great for band gap. Hartree-Fock significantly overestimate the band gap. This is not, RT4 is not a method of choice to get band gap. This is just overestimated. But I think I said enough about Hartree fork in this course, and this course is about DFT, so let's focus on DFT. So one thing I didn't say in the previous lecture on purpose is when I spoke about the failures of DFT, I didn't talk too much about the band gap, but it turns out that in LDA, the band gap is significantly underestimated. And so it's an invitation for students when you want to compare something with experiment. It's a good idea to do this kind of plot that I got from this PRL in 2006. This kind of plot basically represents the target value, which is the experimental gap, with respect to what you obtain, the calculated gap with LDA. And if we had a perfect match, if the two values were the same for every material, then of course all the data points, so the red squares, would all fall on the bisector, which is shown by the dotted line. And as you can see clearly, LDA, the calculated gap, because it's below the bisector, means that the LDA gap is always underestimated. It's systematically underestimated. Which you can say it's nice, it's systematically underestimated, because it simply means that it's certainly a lower value of the gap. But you can also see that some of them are grossly underestimated, maybe up to 50%. Even worse, in these examples that we have on this plot, we see that even some material like HGTE, the band gap is actually much lower, and we even have systems which are in fact semiconductors, so they have a band gap, and LDA predict them to be metallic. When you have a negative gap, it basically means that you have a metallic system where the states are reorganized. Even a simple element like the very well-known germanium, which is essentially the best conventional material for semiconductors, so therefore for transistors, is indeed a semiconductor. If you do LDA calculation on germanium, you will find actually you have a metal, you find a metal. So this is actually not just an exotic issue. It's not an issue that happens rarely, and we don't have to worry about it. It is a serious issue with those approaches. So it's a good idea to always test your band gap when you do calculations. Now, very often when you take a DFT course, you would stop here. You would say, okay, LDA, we know it's an approximation, homogeneous electron gas. We will see actually GGA, which we'll introduce in the next lecture, has the same problem. The same problem being that the band gap is underestimated. We usually think it's about underestimated by about 50%. Is that bad? But so if you are satisfied with this, you can stop the screencast here. But what I want to do for the rest of the screencast is to give you a flavor of the reason why it's underestimated. It's actually a fascinating subject. There are very interesting papers. I will give you one reference that I really like that works on this. But it's a fascinating subject explaining where this discrepancy, this systematic discrepancy comes from. And I think it's pretty fascinating. I personally find that very illuminating. So I'm going to explain that to you for the next 15-20 minutes. So the question I want to answer is, why do we have a band gap problem in DFT? Well, let me tell you first and foremost that one thing that we can argue, and this is an argument you will see often, is that after all, DFT is a ground state theory. Remember, Hohenberg-Kohn was proven for a ground state. So even talking about band gap, where you are really talking about exciting an electron from one state to another, is you get out of the ground state and you say, well, it's okay, DFT is a ground state theory anyway, so let's forget about it. It's okay, it's wrong. I don't think it's a very satisfactory answer from the definition I gave you a few slides ago, because you could consider your system as adding an electron and then consider the ground state of the system with an additional electron, or the ground state of a system when you remove an electron. That's totally acceptable. But even if you take that, if you use that approach, and therefore think that DFT could be reasonable, you do have the problem, and I explained to you. So on top of that, even you can also say, it's another good argument, a good, seemingly good argument, is that the Cohen-Cham eigenstate are fake eigenstates anyway. The Cohen-Cham equations are, it's an ansatz. So just to remind you, it's an ansatz in the sense that it's a fictitious, non-interacting system of electrons, which has the virtue of being built to reproduce the density of the interacting system, right? I hope by now this, what I just said, is obvious to you. That was something that I tried to hammer for the past 2 lectures. So you could say, using the Cohen-Cham orbitals is, of course, it doesn't give you good answers since those orbitals are fictitious orbitals for a fictitious problem. But that's not that satisfactory either, because we can demonstrate a Koopman kind of theorem as well for DFT, where the ionization potential is indeed also minus the energy of the highest occupied molecular orbital. And of course, we are talking about finite system, because if we have infinite system, we cannot talk about that kind of ionization potential and so on and so forth, because in a periodic system, you have an infinite number of electrons, so we have to use a different approach. But let's not worry about that particular technical aspect. So this is where we are. So the eigenstate of the Cohen-Cham equations can be considered as somewhat useful, though they are they actually qualitatively look like what you would measure by XPS, for example, or by different methods. And so this is the important point now that I'm going to try to convince you where the problem of the band gap comes from. So one important aspect, and this, I should probably have highlighted this in color, is that we show that the energy of a system is not simply the sum of all the eigenstate. You would need to go back to a previous slide where we spent, one of the slides with the most equations, if you want to look for it, and the result was shown at the bottom in a red box, where we were showing that the energy of a system of the ground state, the functional in fact, is indeed given by the sum of the energy of the occupied state, Cohen-Cham state, but also a correction related to the external potential, not the external potential, the electron-electron interaction, as well as the derivative of the exchange correlation energy. So I invite you to go back to that if you need to, or you can ask, if you don't find it, you can put a question in the comment, and I will provide you the place and time on the screencast where I discuss that. So already we understand now, even without going too much into the math and the details, that if we go back to what I explained to you as the band gap being the difference between energies of adding one, removing one, and the neutral system, I mean electrons, adding one electron, removing one electron in the neutral system, the band gap being defined by that, we understand that if we do not use the appropriate expression for the energy, clearly we are going to have a problem. And this is actually exactly what's happening. What's happening is that the exchange correlation contribution, which we can show to be the first derivative of the exchange correlation energy with respect to the density, you can actually show that we actually did that for one electron in the previous screencast. If we ignore that, and if that piece changes with the number of electrons, then of course we are missing out. And this is exactly what's happening. So I'm going to try to convince you of this. It may take a little bit of time. I mean, this screencast, as I said when I taught this course live, is probably maybe the most difficult of the whole thing, but I think it's very illuminating given the importance of band gaps in electronic structure calculations. So I'm going to try to tell you a little bit. I just give you the answer, but I'm going to expand on that. So we know only the density has a strict physical meaning in the Cohen-Cham, and the Cohen-Cham eigenvalues bear a semi-quantitative resemblance with the true energy spectrum. Another thing that's also important, and I already mentioned, but I saw it again, is that you will see in the literature, or you will do it yourself, calculated Cohen-Cham eigenstate and show those states, and very quickly, before you know it, you will present that as the DFT result. Sometimes forgetting that those energies are not actually the right energy because that they are from an NSAT. I know it may be a bit confusing, but that's what people do. And I mean, I do it as well. But we have to remember that these energies are actually not they are fictitious energy. But it turns out that in practice, in addition to what the Koopman-Slack theorem that we can use even in DFT, the shape and of those states and so on look very much like what's happening experimentally. That's an interesting debate in the literature, and there's many papers in the conversation about that. So, but I'm not going to go too much into that. I'm going to focus on the band gap. So the highest occupied Kohn-Sham eigenvalue, as I mentioned to you, the Koopman-Slack theorem tells you this result. I already mentioned that to you. And on top of that, you can also show that you can, if you add an electron to your system and look at the ground state of the system with one additional electron, if you will. So it's not a system where you excited an electron, it's a system where you added an electron, so you can calculate the ground state of that. You can also get the negative electron affinity. So in principle, even though we are missing out, we understand that we are treating a fictitious system, saying that, it's a fictitious system, so therefore it's no good to calculate the band gap, this is not an appropriate answer. There should be a way, in principle, using DFT to get the band gap using on the basis of the Kohn-Sham eigenvalue. So let's try to see a little bit more about this, and hopefully I will convince you. And I will show you, by the way, even if there are difficulties following, I will show you one slide at the end that summarizes the whole thing, and it's all you need to know, really. Okay, so the band gap problem, the fundamental issue, is the fact, and this is very important as well, there's a single slide for this, that the thing is that the exact energy functional, so the one we don't know, so if it was exact, the exchange correlation functional, that exact energy functional, this dependence with the number of electrons is actually a little odd in the sense that, and I will say that again, I will show you plots, in the sense that the derivative of the energy, of the exchange correlation energy with respect to the density is not, so the derivative is not a continuous function with the number of electrons. So in other words, you do have a contribution when you compare two systems with a different number of electrons, you do have a contribution coming from the non-continuity of the first derivative of the exchange correlation energy with respect to the number of electrons. That's the fundamental issue. Now, maybe that sounds like a lot of jargon in what I just said, so I'm going to try to explain that a little bit more. So, so we know that Hartree-Fock overestimate the band gap solid, and in DFT, like in LDA, for example, we have a strong underestimation of about 50%. And this is true for both LDA and GGA. But the point is, the main point, and I'm going to explain that in a second, the main point is that problem is not a DFT problem. That problem is an LDA and GGA problem. It's a problem with the fact that we do not know the exchange correlation function exactly. So you can say, well, this is just using words, right? Because since we don't know the exact exchange correlation functional, this is a DFT problem. Well, not so much, because if we were able to define exchange correlation functional better, we would have a better band gap. And in fact, in lecture, not next lecture, but the lecture after next, I will show you some functionals that actually do a pretty good job with the band gap because they treat this problem, they look at this problem. Now here is what matters. The slide that matters is here, and I'm actually not proving this, but I will give you the reference. Before we look at the box that's circled with a black frame, I remind you a result that we've done together, calculating the chemical potential. So the energy that you need to promote an electron to vacuum is chemical potential, so the highest energy, basically, right? We saw that potential is obtained by the functional derivative of the energy with respect to the density, and it's equal to the usual derivative, partial derivative of the energy with respect to the number of electrons. Excuse me. So we've shown that. So knowing this, it shouldn't be too much of a leap to accept the relationship in the framed box, because of course you calculate like a chemical potential like for n plus delta electrons minus the chemical potential like of n minus delta electrons. So it's how do you promote electrons basically. So you get the band gap. There's the energy you need to move an electron that way. So that would be the capital delta on that equation. Now, we are going to look a little bit what we have in that delta and what's the issue we have there. Okay, of course, one issue is that you can always wonder how do you do a derivative if you use the definition of derivative that you learn in Calculus 1. How do you do a derivative with respect to a function that's actually an integer? That's always interesting. So what you need to do is to consider that your system is not just an integer number of electrons, but also a partial electron. So that's become a little bit theoretical, a little bit abstract maybe. So that derivative, it turns out, the derivative of E, so the functional derivative of the energy with respect to n, turns out is not continuous. It is not continuous, at least the exact derivative is not continuous. And as a result, you do have the two values are different, and this is exactly what's happening. It turns out that in an exact exchange correlation functional, the energy with respect to the number of electrons is actually in between those points of integer number of electrons is actually a linear. There's just a linear relationship, and I'll show you on the plot in a minute. Now, this is important because it turns out that property is true for the exact exchange correlation functional. So please, I hope you are not logging off right now because it sounds a little bit abstract. I'm going to show you something. I'm going to show that to you on the plot. It's going to be easier to understand. And this is going to be next. So this plot is basically what you need to know. I'm going to say again what I just said, but with this plot, I think it's going to be clear. So first of all, I want you to focus on the black line, which is the exact, if you had an exact exchange correlation functional, it is how the energy would vary with the number of electrons that you put in your system, which is exactly what we're interested in. So we have the dots, the black dots. Actually, you don't see the one in the middle because it's behind the red dot. Those are the values with integer number of electrons. Now you can show that the exchange correlation function, the exact one, would actually have those straight lines in between those points. This is what's in black. This is the exact result. Now, the functional we use, like the local density functional approximation, but it will also be true for the functional we'll introduce in the next lecture, so the GGA, the generalized gradient approximation. Those functional, they do a pretty good job with the energy, actually. Look, these are the red dots. The red dots, those values with the value of the energy for the number of electrons match pretty well the exact functional. And we know that because we know that LDA and GGA are not doing bad at all. They're not doing bad at all for the total energy. Sure, it's not perfect, but it's pretty good. And remember why it's not bad at all. It's not bad at all because the largest chunk is treated exactly as P as part of the independent piece of the independent approach of the energy. Now, of course, the errors you make is because you don't have the exact exchange correlation functional. Now, the most important point, it may be subtle, but it's key, is that those functional like LDA and GGA, which were not designed for bandgap, let's remember this, they were not designed for this, right? They were designed just to provide a functional that works and that's kind of tractable. It turns out that those functional, if you were to look at what happens for a fractional number of electrons, they are continuous. So the function is continuous. Of course, the black function is continuous too, but the first derivative is not. If you calculate the derivative of the black line on the left of the central point or the right of the central point, they are not the same. So basically that means they are not continuous. And that discontinuity is actually part of the band gap. Now, if you look at LDA and GGA, the derivative on the left and on the right of the red dot is the same. The function is continuous and the derivative is continuous. Therefore, you are missing out this discontinuity in the derivative. And you can show that exactly. And in fact, if you were to calculate all this, and I'm sorry that I'm showing the screen all at once, but I'm not going to go too much in the details, but it's just to give you an idea, is that it turns out that the Kohn-Sham gap, so the capital delta Ks that's defined on the top, which is obtained from indeed this energy difference between the highest occupied state and the lowest unoccupied state, so epsilon n plus 1 minus epsilon n, comes from the functional derivative, the change in functional derivative of the kinetic energy of the independent electrons. Okay. Again, I'm not proving that exactly. You can actually show that fairly easily yourself by going back in the Kohn-Sham equations. But don't worry too much about that. That's not the point of the message I'm trying to convey here. The thing is, the actual band gap, the capital delta that I repeat that in the frame box, that true gap has indeed the capital delta Ks, but on top of that, it has this delta Xe, and this delta Xe comes from the fact that the derivative of the exchange correlation functional is not continuous, what I just showed you on the previous slide. In other words, to summarize all this, the actual band gap, that's exact band gap really, the capital delta, is not just the delta Kohn-Sham, but also a contribution from the fact that the derivative of the exchange correlation functional is not continuous. This discontinuity is quantified by delta Kc. So, as I just showed you on the plot, this discontinuity in the derivative of the exchange correlation energy functional, is zero in LDA or GGA, for example. Therefore, we are missing out totally the capital delta Xc. And since the delta Xc is always a positive number, we are always underestimating the band gap, right? This is essentially the main thing that you have to remember, and I want to show you. I think it is so illuminating. I think it takes a little bit of time to wrap your head around this, but this is really the mistake that we make, is this missing out this derivative discontinuity. Now, this is kind of nice. Why is it nice? Because people who design exchange correlation functional, I mean, the heroes of DFT really, and I will introduce names coming up in the next lecture, they know this. They say LDA or GGA were not designed with that in mind, those functional derivatives. They were not designed with that in mind. But now that you know that you have that property that exists for the exact exchange correlation functional, you can now design functionals that have that property, and of course improve the result. And you can say it's a subtle property, but hopefully you understand it with the background that we have covered in this lecture series. So that's nice. You can also calculate those derivatives. You can also calculate, if you can calculate them right, you can calculate the ionization potential, you can calculate the electron affinity. And so it turns out that those issues, those difficulties led to a lot of debates about the meaning of the eigenvalues, or the Kohn-Sham eigenvalues. But I think at this point, we cannot just say, oh, the Kohn-Sham eigenvalues are meaningless anyways, therefore not having the right band gap is normal. That's pushing it too much. The electronic structure using purely the Kohn-Sham orbitals is indeed a fictitious system. However, those states, those high energy state and so on, in Kohn-Sham have a meaning. And if you have the right exchange correlation functional, you can actually get the right band gap. So this is a little bit too easy to get out of the problem by saying Kohn-Sham orbitals means nothing anyways. That's too easy. That's the message I want to tell you. Now I want to show you the plot that you probably should remember if you want to remember anything from this screencast, which summarizes everything. It turns out that the energy that the true band gap, so the capital delta without any subscript, which is on the right-hand side there, is the energy you need. This is the energy difference between the highest electron for n, the highest energy for the electrons for n electrons in the system, with respect compared to the highest occupied molecular orbitals for the system with n plus 1 electrons, right? This is exactly what you can show there with the blue arrows. The highest occupied molecular orbitals for n plus 1 is actually not the same energy as the lowest unoccupied molecular orbital for n electrons. When I talk about HOMO and LUMO here, of course, I'm talking about the Cohen-Sham state. And the difference between them, and it's really due to exchange and correlation, the delta XC is what you are missing out. So in this plot, for example, I'm showing you the values of I'm showing you the values where delta KSC is about half of the delta KS. This is actually an optimistic case where, so the mistake we make is about 25%, 30%. Usually that's larger than that. Also see that the ionization energy is correct. The electron affinity using Cohen-Sham would only be correct if you actually could calculate with n plus 1. And I hope this is useful. Now, one thing I want to tell you is, like, one thing you can remember essentially is the true band gap is the Cohen-Sham band gap plus delta XC. Now, it so happens that there are some cases in strongly correlated systems, so those where the correlation piece is a significant amount of the energy, where delta XC is much, much larger than delta KS. In fact, delta KS would be 0, but delta XC is significant. And there's a class of quite a few materials like this, the strongly correlated materials, where DFT is not the greatest, at least in LDA or GGA. One example is the Mott insulator. Mott insulator that are only insulator due to correlation, exchange and correlation effect. And in that case, in the case of the Mott insulator, the band gap, it's an insulator, as the name says, but the band gap is solely due to the exchange and correlation piece of the DFT problem. So if you were pick a Mott insulator that you want and do a DFT and LDA calculation, you will find a metal. That's basically what it says. So that's interesting to know. So, this is all part of the culture of understanding DFT. And more importantly, to be careful. DFT is great, but there are approximations. Some of them are well known. Some of them are a little bit more subtle, but you can look at that. So one paper I really enjoy reading about this, and I really invite you to read it if it's something that's of interest to you, is this paper in 2014. There are other papers as well, but this is the paper I used to give this summary. It's really a summary of this, but if you want to learn more, I invite you to read this very well-written paper that explains all this idea of this fractional charge and so on, and what we can actually look at to get a good exchange correlation function. Just to get an idea, I put this is one of the figure of the paper. The exact one is again in the black curve. It's FCI, which means full CI, which is beyond Hartree-Fock approach, which is actually essentially exact. And you can see that comparing the full CI with all the other methods, here we only have two. We have PBE is a GGA approximation, B-TRILIP is a hybrid functional Hartree-Fock in the red one. You see all that, all the others are pretty much do not represent this sharp changes that we can find in for example, in the full CI. This is actually for the system of a hydrogen atom. So I hope this was illuminating. If you had just one thing to remember, is that yes, the band gap in LDA is not great. because we are missing out this discontinuity in the first derivative of the exchange correlation energy with respect to the number of electrons. That's basically the reason for that. It is not just because DFT is a ground state theory, or because Kohn-Sham orbitals are no good. That's not the reason. If we had exact exchange correlation functional, we could calculate the band gap. Thank you very much for your attention. I hope you enjoyed listening to this as much as I enjoyed talking to you about it. See you later.